Recording.
Okay, so it's my great pleasure to introduce Professor Jaqueline Godoy Mesquita. She is a professor at Universidade de Brasília in Brazil, and also she is current the president of Brazilian Mathematical Society. And today, Professor Jaqueline is going to talk about a new concept of periodicity. So thank you very much for accepting and deliver a talk again in our seminar. And it's a great honor to us hear you again.
Thank you very much, Diego, for this nice introduction. First of all, I would like to thank the invitation. It's a great pleasure to me to be here. So I would like to thank Professor Juan Limaco and also the other organizers for this invitation. It's a great pleasure to be again in this nice event of this seminar. So thank you very much. So, okay, today I tried to bring here such a type of general concept of periodicity. Usually, many people work with periodicity, and today I will try to talk what's the motivation in order to have a more general type of concept of periodicity. And I believe that it would be very nice for those who works with periodic functions and any type of equations that you have. So let's see. So first of all, my co-authors here, just to introduce the co-authors. So Professor Martin Bonner from Missouri University of Science and Technology, and Professor Sabrina Strapert from University of Pittsburgh in United States. So both are my co-authors in this subject of periodicity. And I would like also to mention that we worked very hard in this topic when we were in Oberwolfach. So I would like to thank here our stay in Oberwolfach. So here it's me and Sabrina discussing a lot about this subject. And yeah, you see what's the motivation behind of it. So here it's my picture with my co-author, Professor Sabrina Strapert in Oberwolfach. So first of all, in order to be able to talk about this periodicity, I will introduce some theory that's about time scales calculus. So this is a very recent theory, and it was introduced by Stephen Hilger in his PhD thesis in 1988. And the main idea behind of this theory was to unify the discrete and continuous case. However, what we have is that since a time scales is only a closed and no empty subset of the real numbers, we can have a much more types of equations. In this case, not only discrete ones like the difference equations, and not only the differential equations, but we can also have the hybrid types of equations and also other types of difference equations. So we can have many types of equations that we can investigate it when we deal with time scales theory, since we can have not only included in this theory discrete and continuous, but much more inside. Here only to mention that Bernard Albach was the supervisor of Stephen Hilger, and here's his also picture because he also had a very important role in this theory also. So here, as I mentioned before, we can have that a time scale is a closed and no empty subset of the real numbers. And then we can have many types of examples. So if we are in the integers number set, we can have the discrete case. So that's many people usually work, that's the difference equations. But also we can have that the time scales could be like HZ, that usually it's very used when you deal with numerical simulations. So when you have that, for example, 8 goes to 0, we have that this time scales HZ also converges to the real number set, and then we can have some relations between the discrete and continuous. So usually people that works with numerical simulations work with this type of time scales in order to understand the behavior for the continuous one. So they discretize using these time scales, that's 8z. And then since they know that 8z goes to the real number set, so when 8 goes to 0, so they use these facts in order to know a little more about the solution. So it's easier to calculate the solution using numerical simulations for the discrete one because it's only interaction. And then in order to know a little more about what happens with the continuous solution, sometimes you can do like this convergence for the 8. So it's again another example of time scales, but we can also have much more than that. We can have such a type of time scales that you have a discrete and a continuous at the same time. So you can have like intervals union with points. So we have both situations like discrete and continuous. And also we can have the counter set that's much more complex, and it's very important in order to have some counter examples. So we can have a big variety of time scales when we deal with this theory. So, and in order to understand better about this theory, because the main idea behind is like to unify the concepts that we have for the discrete and for the continuous in order to put them in a one framework. And you have as a special case for the discrete and then for the continuous case. So here, when we think about that, so we can have a more general here, derivative, integral. So we will show you about these concepts. So in order to be able to present these concepts, we will start with some operators here. So we have this first operator, this rho, that's the supremo of the points in the time scales, such that it is smaller than t. So rho of t is something like that. And we have that this forward jump operator, that's the sigma, is the infimo of the points of your time scales, such that's bigger than t. So this is called the backward jump operator, and this one is the forward jump operator. And then what we have is that the grayness function will be the difference between the forward jump operator and the identity. And since by the definition of this sigma here, the forward jump operator, we have that the forward jump operator is always bigger or equal t. So sigma of t is always bigger or equal t because of this definition here. So this difference here will be always bigger or equal 0. So that's why we have this mu that goes from the time scales to here. So we have this definition that will be the difference. And then, as I mentioned before, we can have like continuous and discrete. And because of that, we also can have some concepts for our points in the time scales. So we could have like a right dense points and right scattered points, left dense points and left scattered points that we will define using these operators. So if sigma of t is equal to t, we say that this point t is right dense. If sigma t is bigger than t, then t is called right scattered. And analogously, we have this for the background jump operator. So rho of t equal t will be left dense, and rho of t is smaller than t, we have that's left scattered. So we have these definitions here when we deal with time scales. Then using that, we have here the definition of the derivative. So here, this derivative is more general than the usual one because it encompasses the continuous case. So for the case that we are used to deal like the real number set. So here we say that a function is delta differentiable and if it satisfies this inequality. So if you see, it's very similar what we have for the continuous case, but here we have this sigma of t, that in the continuous case, sigma of t is equal t because all the points are right dense. And here, then we have exactly the same definition that we have for the continuous case. However, when we are in the discrete case, the sigma of t is not equal t. So we can have much more different types of derivatives that needs to coincide with the ones in the specific case. So for example, when we have the zeta, so we have a different type. And again, this definition can encompass the derivative for the discrete type. And here, first we will start with a concept of isolated timescales, because this was our first ideas first in order to investigate it about periodicity. And we will say here that the time scale is isolated if all points are right scattered and left scattered at the same time. And also we'll use this notation here. So when appear F sigma, it will be the composition of F and sigma. And then we can have many properties very common that also we have for the continuous case. So here we have this formula that sometimes it's very useful when we are trying to do some calculations. Also, we have the product rule that in fact, it will be the same when we are in the real number set, but also it could be different when we are, for example, in the zeta or in discrete case, when sigma is not equal the identity. So here we have this equality here for the product rule. And also here the quotient rule, we have this equality. Again, when we are in the real number set, we have that this one coincides with the usual one that we are used to deal. Also here, in order to be able to talk about time scales, it's really important to define what's the regressive functions. And here we say that a regressive function is a function that satisfies this statement. And here, if you see, if we are in the continuous case, so this is always satisfied because we have that the gradients functions is equal 0 because sigma of t is equal the identity. So here we have that if we are dealing with a regressive functions, we have that for the continuous case, all functions are regressive. However, when you deal with other types of time scales, so it's really important to consider that in order to be able to define the exponential function. And we will denote the regressive function set by this R here. And here's all the functions that are regressive, that satisfies this statement for all points in the time scales. And here, in order to ensure that if you sum two regressive functions, you have a regressive function, and if you subtract two regressive functions, you still have a regressive function, we need to introduce here some operations. That's first is the sequel plus addition. That's this one here, that it's like P plus Q plus mu P Q. And here it's important to mention that in the real number set, here the mu is 0, so you have the usual sum. However, if you are not in the real case, it's really important to have this type of addition in order to ensure that if you sum two regressive functions, you are still with a regressive function. And the same happens here with the subtraction. So the subtraction is given by this identity here. And again, if you are in the real numbers, since mu is equal 0, so you have the usual subtraction here. So also here, what we have is the definition of the exponential function. And in order to be able to define the exponential function, we need to work with the regressive functions here. And here we define in the same way as we define for the real number set, and as the unique solution of this initial value problem. So here, the exponential function of our time scales will be given by the unique solution of this problem. And here we have several properties concerning the exponential function. So here are some of those properties. Okay, and also we have a type of variation of constant formula for the time scales. So using now this exponential function, so the unique solution of this initial value problem is given by this integral here. Okay, so but as I mentioned before, I am very interested here to talk about periodicity. And then I will start talking about periodicity on isolated timescales. And why that's a challenge. So you can think, for example, okay, when we are in the Z, we know what is a periodic function. So a periodic function, you all have like a P of a T plus omega is equal P of T for all T in the time scales. And then we have an omega periodic function. However, what happened here is that sometimes, depending on your time scales, T plus omega does not belongs to the time scales. Even if T belongs to the time scales, you cannot ensure that the T plus omega belongs to the time scales. So here it does not make sense to talk about periodicity in the usual sense. So that's why it came a big challenge about how to define periodicity for all types of time scales. Because the main idea behind of time scale is to unify. But when you're dealing with a periodicity, we could not unify because we needed to work with some time scales that has the additivity property, like a T plus omega belongs to the time scales if a T belongs to the time scales, and we needed to exclude the other ones. But this is not nice because in the theory of time scales, what we want is to unify all this theory, all time scales. So in order to do that, we needed to think how we can unify the concept of periodicity to all types of time scales. So then we started with the isolated time scales, the ones that have all right scattered and the left scattered points at the same time. And we tried to generalize the concept of periodicity to this specific case. And then we generalized that to all time scales. So I will talk about this now. So, but first, before to talk about periodicity on isolated time scales, I need to introduce what is the iterated shift. So let's see. So here we will define as this new the iterated shift, and it will be like the composition of the for-all jump operator omega times. So here we compose sigma with sigma and so on, omega times. So this we will denote it by this new, and it will be very important in order to have the omega periodicity. And then here, as before, this F nu now will be this composition, F composed with nu. And then when we have like F nu sigma will be like F nu and sigma, like these two compositions. And here, if you see, of course, we can change the way, like we can first compose with sigma and then compose with nu, and it will be the same. And so we have this here. And also we have the sigma and nu commute. So we have this, it's equal nu composed with sigma. And we can rewrite in this way here what this notation means. So, okay, now with these iterated shifts, we can talk about periodic functions on isolated timescales. And then what's happened here? So we have here this P is an omega periodic if we have this equality here. So here is the derivative of this nu, and this is multiplied by P composed with nu, and this is equal P. If we have this happening for all time in the time scale, we say that a function is omega periodic. And we use this notation here in order to denote all the space of all omega periodic functions. And then we can have several properties concerning these. But first, let's see if this definition is good or not. So here, when we try to see some examples for this case, what we have is the following. So here, if we have these time scales, then what we have, so we have one point is t, and the next one, if you see, will be like a key multiplied by t, so qt, and the other one will be q squared t, and so on. So here, when I compose omega times like sigma omega t, so I will have a q to the omega t. So I have that p q to the omega t, and the derivative of this will be q to the omega. Then here in this case, I have that p is omega periodic if it satisfies this equality here. And here, if you see, it's the same type of definition that was introduced by Martin Borne and Xiao Shan for the omega periodic function for this specific case. When we deal with these time scales, we say that we are working with a quantum calculus. So here is a specific time scales, that's a time scales of quantum calculus. And this is very important for applications in quantum physics in many types of phenomena when we deal with quantum physics. And that's why it's very important, these time scales. And the main difficulty was to find some definition that we could unify this type of periodicity. That's not simple, if you see, and the usual one that we have like that. So it's not so easy to see how could we define in such a way that we could unify both. However, here, if we do the derivative of the one that's here inside, and here inside we are like composing omega times the sigma, so we have here that we have this unification for all isolated timescales. So here we have this one for all times here. And now if we consider HC, what we will have that if we compose omega times the four-hour jump operator, so the first one will be like a t plus omega, and the second one will be, it will be like a t plus 2 omega, and so on. So here we have like t plus h, t plus h. When you do like sigma of t, you have t plus h, and then if you do that omega times, we'll have like a t plus h omega. So what we have exactly here. And then when you do the derivative here, what we will have, that the derivative will be 1, and then it's the one that's multiplying here. So we have that p of t will be equal p of t plus h omega for all t on the time scales. So is what we have. And then here, if we are in the zeta, what we have is like the sigma t will be t plus 1. And then if I apply that omega times, I will be that sigma omega of t will be t plus omega. And then if I do the derivative, it will be 1. And then I have this equality. So this definition seems to be very nice because it coincides in all those situations with the ones that we had for these specific cases. However, here, if you see, we are only working with isolated time scales. And why that? Because when we are dealing with real numbers, for example, what happens is that the sigma, if we come back here, the sigma of t is equal t. And then if I compose that omega times, it will be sigma of t will be sigma omega t, and it will be equal t, because since each one here is equal t, so if I compose omega times, I will still have a t. And then here, if I have this t will be like a p of t will be equal p of t, and there will be, in this case, all functions would be periodic. So when you're dealing with the continuous case, this definition in this way does not make sense. So we need to think how to define for any types of time scales in a general sense. But we need something more, not exactly this definition when we have this new is exactly the sigma function, because sigma in the continuous case is equal to identity. So it doesn't matter if you compose this omega times or 3 times, it will be in the end the identity. So it will have only the trivial equality, and it's, of course, it satisfies for all functions. So in the continuous case, if we use that, it does not make any sense. However, for the isolated time scales, it makes all sense, and we can encompass all types of isolated time scales. So we can recover here this type of periodicity and also the other ones. And here it's really important that we have many of properties of the periodic functions. Okay, but as I mentioned, I would like some general definition that also works for the continuous case. And then this motivated us to define for the continuous case in this way here. So we have that new now, it's not the sigma, but will be a differentiable and a strictly increasing function. So using now this definition, we can have that a function is periodic with respect to new if this is satisfied. So we will see that depending how you define your new, we can recover the usual one. Yeah, okay, the periodicity that we know, but we can have a much more than that. So we can have other types of functions that have some similarities with the periodic functions, that some properties that comes from the periodicity. So here we will say that a function is periodic with respect to new, provided this equality is satisfied. So you will denote it by this one, the set of all periodic functions. And here it's nice because, again, now if you define your nu of t equal t plus omega, this is a type of differentiable and strictly increasing function, and the derivative will be 1, and we will have the usual one for this specific case, but also we can have a much more than that. We can have other types of periodicity. So here, if we choose our nu as t plus omega, as I mentioned before, so in the case that we are here, so we have that this definition collapses to the classical definition that we have for the continuous case. And then we have that this reads like that. So, and here, only to mention that it's important that we do not need to ask that our f is continuous function. So, for example, if we think about the Dirichlet function, and if we think that omega belongs to the rationals here, so we have that the Dirichlet function will be a new periodic function. So also we will have this property here. So also we have that the constant function will be omega periodic, new periodic for this specific one. So this new. So we can have, of course, if c is equal 0, or if we have this new t equal t plus c, And then we also have this constant function will be periodic. Also, we can have a more different types of periodic function. For example, we have that this function here is not periodic in the classical sense. However, here, using this definition of periodicity, we have that this function f is periodic if we choose our new, like this ln e of t plus omega. So in this case, specific case, we have that this type of function is new periodic. So we have that's periodic in this sense. Also, we have that the trigonometric functions also will satisfy our situation of periodic function, that they will be periodic function in our case. But here we needed to consider our new, like a t plus 2p, 2 pi. So using that, we have that these functions continues to be periodic functions in the classical sense. So we also, as I mentioned before, if you have like a t plus omega, if you take our new like a t plus omega, we have that we recover all the omega periodic functions in the classical sense. But we can have a much more than that. We can have more types of periodic functions. And here also we have a very nice property concerning the integral of a periodic function, the same way as we had before that we have in the classical definition. So here, if we define our capital F nu of t equal this integral here, t until nu of t, f tau, delta, the tau. So what we have is that here the derivative of this will be equal this, but if you see here, if this small f is omega is new periodic, so this is equal 0. So that what we have is that this is constant, this f of nu, the same way as we have for the classical definition. And it motivated us to define the periodicity in this way because we recover this property that it's very important. So if we have like in the classical case, like nu of t equal t plus omega, so you have that this integral t to t plus omega will be like constant. So the same will be happen here. So we have that if this small f is new periodic, so what we have is that this part here is 0 using our definition. But this is 0, it means that this derivative is 0, so this function here will be constant. And this function is exactly this integral here. So, and here is only using the chain rule so that we have this equality. And okay, here is the proof of that. It's only, as I mentioned, so if you define your 8t equal this integral, of course, you have that this f nu will be equal this difference here, and the derivative using the chain rule will be given by this. And then using the fact that 8 is defined by this, we have the derivative will be the small f, and then we have this equality. So it's very direct proof. Also here we have this other property that the same happens when we have in the classical sense, so about the integral of a periodic function. So here we will have that the same will happen here. So for example, if you consider your nu of t equal t plus omega, to integrate t until t plus omega is the same to integrate t0 until t0 plus omega. And of course, it will follow as a consequence of the previous theorem. So we'll be very direct again. And here we can see also other types. As I mentioned before, in our sense, this function here is periodic. If you consider the nu given by this function here, then what we have is that this integral here will be equal this other integral here because now we have this nu of t is given by this. And then calculating this integral here, what we have is exactly that. Then this cancel here, and then what we have is omega, but this is the same if we sum and subtracting this exponential function. And again, this is exactly the same as here, and this is exactly this because of the definition of our new function. So we have here this equality. So we have this property. Also here, we have this other property, so that also we can see this property when we deal with on the classical case. So if you integrate it from A to B, so it's the same to integrate it from nu applied to A until nu applied to B. So we have this equality here. And here, again, it's only using some usual properties. We can see that it again happens. And here, again, if you have one function is new periodic, then it's also new composite to new periodic function. And it's very simple to prove it. Again, it's only using the definition and the composition we can see that, in fact, it happens. And again, if you have two different functions, that's a new periodic function, we have that the linear combination of this function is also new periodic function. So it's really important to us, yes, when we deal with this type of functions. And then we have these properties. It follows like very direct again. And also we have many other properties, but here one that's very important is that the product of two new periodic functions is not necessarily new periodic. And here it's nice because we have some different things and we need to be careful in this type of situations. So here I would like to mention about some next steps that we have in that direction. So as we saw before, we have this concept for the continuous case, but also we can generalize that for all types now of time scales using this definition that you saw before, like your new now is an increasing function. And then we can also generalize it for any types of time scales. And the nice things that if you remember before, I introduced here the regressive functions that are very important when you deal with time scales. And the good thing is that the periodic functions, periodic and regressive functions, is a type of subgroup of regressive functions in the sense that if you sum two periodic and regressive function, we can have that this is a periodic function. And the same happens with the subtraction. So it's really nice, and we can see that it is really fits in the classical definition of time scales, and it can generalize the sense of periodicity for the continuous case. So we can have something more general, and we can investigate it, the possibilities for those types of functions. And we started by investigating some properties concerning these functions with these properties, so we can prove such a type of a periodic averaging principle for this type of functions that are periodic in this sense. And it's really nice because we didn't know before how to apply like averaging principle for certain types of functions. And since now we encompass all those types of functions, we can apply the periodic averaging principle for those types of functions. And it's nice because we can investigate more complex types of equations using these approximations. So, and now there are several things that it's possible to do. And for example, once you have these periodic functions, and what about almost periodic functions? So is that possible to generalize in that sense? So this is a completely open question, including the sense of time scales. So it's really nice to try to think how to do that. Even in isolated timescales, we don't know if it's possible to generalize in something that direction in order to include all types of almost periodic functions. The same concerning almost automorphic functions. So there are a lot of open questions in that directions. So I hope that if you work with partial differential equations or evolution equations, you always want to know a little more about periodicity. Some moments you need to look for periodic functions, periodic solutions for your systems. And I think this type of a new concept can open a road in these investigations. So this we have some future projects together with this my two co-authors in that direction. Here it's in the past, now she's in Pittsburgh in United States, not in Australia anymore. Yeah, so that's it. Thank you very much for your attention.
Okay, thank you very much, Jaqueline, for your nice talk, very nice talk. So now we open the turn for questions and comments. Okay, Jaqueline, a little question. Do you have a practical application of that in mind? Can you
Yeah,
explain?
yeah. Actually, we made some applications for